Welcome to this Part 2, Computational Chemistry for Experimentalists, Module 6, Lab Practical, Heats of Formation of Ethylene. So here we are on our remote desktop calculation. We're going to make a new spreadsheet. New spreadsheet sheet. Heat. So atomization, energy, and heat of formation of ethylene. Now again, we're going to need to have, so the different columns are going to be different methods. The different rows are going to be different energies that we need. So here we're going to have the computed enthalpies of, let's see, carbon atom, hydrogen atom, and C2H4 ethylene. I'm going to illustrate for this for just one method. I'm going to do the B3-lip DFT using the 321G basis set. You'll need a larger basis set to get a reasonable result, but this is the basis set we'll use for illustration. So our first step is going to be the carbon atom. Now I'm going to do a new input file. So we're going to do B3-lip 6321G. We're going to do a vibrational frequency calculation. And this is going to be carbon ground state, carbon atom. Carbon atom in its ground state is neutral. What is the spin multiplicity of ground state carbon atom? Well, you could check a couple of different values. Let's do that. If I didn't know what should be the ground state if I wasn't sure whether a ground state carbon atom should be a triplet or a quintet, I could just compare the results. This way. Just as an aside, improving our self-consistent field convergence might be useful, so we can save those. We're going to save this file as CB3-lip. Now I'm going to run that calculation using Gaussian. This will take a little while because I'm actually going to be doing two separate calculations, one on the triplet, one on the quintet, just in case I wasn't sure what my total energy should be. Look at my log file. Let's see. My first SCF done. Run. Minus 37.64269. My second. Oops, didn't run. Okay, I was missing the you must have a blank line at the end of the file. But anyway, we'll just run that in a second file and we'll say, alright, well, if this triplet is really the true ground state of carbon atom, what we can say is in our thermochemistry, sum of electronic and thermal enthalpies, the same number that we had before. I'm just going to copy that guy and put it here. If I need to, I'm going to update that, and I'm going to check if I need to update that by just finishing this up. Do multiplicity 5. Save as. And 5. Run that calculation. Blah blah, and look at this. My sum of electronic thermal enthalpies minus 37.467 Hartree per particle, substantially less negative than the minus 37.6403. So this level of theory predicts what I believe is seen experimentally, that carbon atom is a ground state triplet. Isolated carbon atom is a ground state triplet. Okay, now I'm going to do the same thing for hydrogen atom. Calculation here. This should run fairly quickly because it's just hydrogen atom. I want to point out something here. Okay. Point out a couple things. So here's my log file. If I look at this, I find a couple of interesting things that I want to illustrate for you. First, the total energy is not quite as negative as the exact value. If I do a DFT calculation, I could get energies that are below the exact value. It's no longer exactly variational the way Hartree-Fock theory or ab initio theory is. Second, there's a correction that I'm building in by doing this vibrational frequency calculation. There's no such thing as a vibrational frequency for an isolated atom. What I'm doing is just Gaussian will automatically build in all of the 0-point and thermal corrections that I need. The thermal correction to energy, the thermal correction to enthalpy. These come from various tricks that are built in, so I'm just going to grab this number, sum of electronic and thermal enthalpies, which is not quite as negative as the total energy, but that's what I need here. Now, C2H4, I need to build ethylene and run the calculation on ethylene. So now, finally, after 45 minutes, now I need to use Gauss view. And I'm going to use Gauss view just to build an initial guess at the geometry. It's going to be a bunch of stuff. I don't care. I'm not going to run Gaussian from here. Now, ethylene. Up here in Gauss view, I have these fragments. There's ethylene. I'm going to save this on my desktop. As C2H4, B3 lip, C2G.GJF. And now, this is not a B3 lip calculation. I didn't make that change. All I needed was geometry. I'm going to go and modify the input file by hand. This is what Gauss-View wrote for me. It said something about the checkpoint file. I'm just going to get rid of that. But now I need to use the same method as before. B3 lip 321G. And now I'm going to optimize the geometry and then compute the vibrational frequencies, just the way we did for methane at the beginning. All of this stuff I can ignore because I deleted the geom equals connectivity, which is just there to draw little sticks in Gauss-View. It has nothing to do with the Gaussian code. Save this, run it here. Now I'm doing a geometry optimization, and it's on 6 atoms rather than 1 atom, so this is going to take substantially longer. So I have to just sit and wait for this. And then the next things that I'm going to need, I just want to introduce this. You have to start thinking about a little bit of undergraduate physical chemistry to get these results. The heat of formation of a molecule is the enthalpy change for forming the molecule out of elements in their standard state. The standard state of hydrogen is H2 gas, and the standard state of carbon is solid diamond. So if we wanted to compute that directly, what we'd have to do is we'd have to compute the enthalpy or ground state enthalpy of C2H4, we'd have to compute the ground state enthalpy of H2, and then we'd have to compute the ground state enthalpy of diamond, which would be a complicated periodic boundary condition calculation. Instead, what we do is we compute the total enthalpies of carbon atom, hydrogen atom, and the molecule that we're interested in, and then we combine those with experimental values of the enthalpy of formation of the atom. So we make a whole thermodynamic cycle to get the number that we want. What I recommend is that you actually draw a picture of that thermodynamic cycle that we need. Draw a picture in the results or discussion section of your lab report and say, this is the number that we're actually computing. Regardless, here's my results. Here's my B3 lip 321G. I scroll all the way down to the bottom, blah, 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 blah. Calculation optimizes, I get vibrational frequencies. All the way at the end, I get that thermochemistry analysis. So here's my sum of electronic and thermal enthalpies. Copy this guy. Paste it in here. And now I get to compute the atomization enthalpy, which is going to be I'm going to convert that to kilojoules per mole. It's going to be the enthalpy of C2H4 molecule minus twice the enthalpy of carbon atom minus 4 times the enthalpy of hydrogen atom. So that is the enthalpy change predicted for forming C2H4 out of isolated atoms. So now we can also have the experimental enthalpy. I'm going to put this on a different line. Just as an aside, I should put units here. So this is in Hartree. Hydrogen atom total energy is in Hartree. C2H4 is in Hartree. Atomization enthalpy is in kilojoules per mole. Just an aside, I told you that there is these small corrections that are built into the thermochemical analysis, even for the isolated atoms. So there's a thermal correction to the energy for carbon atom, and there's a thermal correction to the enthalpy for carbon atom. And my question is, are those real? For the Gibbs free energy, it is real. Oh, thermal correction to energy, I'm not sure. The thermal correction to enthalpy is H is U plus PV, so we're doing corrections for temperature 298 Kelvin, pressure 1 atmosphere. So PV, U plus PV to get to H, that's where this number comes from. Thermal correction to UB is U plus PV minus TS, so that's where this number comes from. There's a TS that we assume isolated atoms at T, 298 Kelvin, S, we get from statistical mechanics for isolated atoms at this pressure. Thermal correction to energy, I'd like you to try and figure out where does that number come from. Double check it. Double check where the thermal correction to energy comes from for atoms. But alright, anyway, experimental enthalpies of formation. Carbon atom in kilojoules per mole and H atom kilojoules per mole. You'll need to find those numbers. You'll need to find some reference values. And so we get the heat of formation is going to be, so carbon atom, let's just look up atom enthalpies of formation. You'll want to get an actual reference of these, but standard enthalpies of formation of gas atoms in kilojoules per mole. We're just going to grab these numbers. I'd like you to try and see if you can find a better reference, but I'm just going to grab these. So hydrogen is 218. Carbon is 717. We have to check the signs here, so that should be this plus 2 times that plus 4 times that. Double check the signs here. Please make sure you get the signs right. Sign errors are something that I always struggle with, so I'm not going to guarantee that what I'm doing right now is right. But heat of formation of ethylene is 87 kilojoules per mole at this level of theory. Let's just double check. Gaseous ethylene. Standard enthalpy change of formation of gas phase ethylene is plus 52 kilojoules per mole. We got plus 87 kilojoules per mole. We're in the right ballpark, and as we go to better basis sets, different methods, and you're going to check different basis sets, different methods, and you're going to reuse these experimental enthalpies of formation of isolated atoms over and over and over again. And you see how. So here we can say the literature result for this, if we trust Google, 52.47 kilojoules per mole. So you see, we're not quite right, but we're in the ballpark. As we go to better basis sets, that should get better. If we do the MO62X DFT, it should get a little better. If we do coupled cluster theory, which you could do, that would get even better yet. I want to give you a suggestion. It's possible to do, for example, CCSD, CCPVTZ, it's possible to use the geometries and thermal corrections for one method to add them to the total energy of another method. How would you do that? Jumping back here again. So the thermal correction to the enthalpy, 0.002360 Hartree. That's for carbon atom. You just see carbon atom we have 0.002360. For hydrogen atom we have, my goodness, thermal correction to enthalpy, which should be just PV plus some other fancy stuff, is the same number. And for C2H4, it's much larger. So if I get energies here at those fixed geometries, I can get enthalpies by just saying it's equals this number plus that one. So I can do a coupled cluster calculation at the fixed B3 lip geometry and use the geometry and the 0-point energy and thermal corrections from that lower level calculation, and that will save me a lot of time. Let's just illustrate that right now. Let's just illustrate that right now. And I'm going to show this to you for the let's just illustrate that right now. So the first thing that we need to do is grab the computed geometry. So where's the optimized geometry from this calculation? It's right here. So 6 atoms. We're going to copy that, make a new input file, and paste that. So this is the B3 lip small basis geometry of ethylene. Now I'm going to do coupled cluster singles and doubles, coupled CCE, PVT, Z, basis set. Now this calculation is going to take a pretty noticeable long time. If I had to do geometry optimization, it would take way too long. This calculation is going to take quite a significantly long time. Coupled cluster, even before adding perturbative triples corrections, coupled cluster takes a long time to run for this. Even just a single point energy. If I tried to look coupled cluster geometries, I'd be here forever, which is why we don't do that. But we're going to just let this guy run and run and run. And then we're going to plug in the values and see how much do we actually get closer to the experimental enthalpy of formation of the gas phase species. Do we go from 87 kilojoules per mole to something that's a little better? Well, calculation is done. That's nice. open that log file. Scroll down. Just as an aside, I could do the same thing with Hartree-Fock theory at those geometries, because each time I do a coupled cluster calculation, I start with a Hartree-Fock calculation. So, excuse me. So for this, I'm going to scroll down, 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 down. There's my Hartree-Fock energy, which I could put here for C2H4. Now you're starting to see, hopefully, also why I need so many, why I want to use a spreadsheet to do this rather than just trying to do this all by hand. These are my thermal corrections. They're going to be always in column C. Column C. So now I can copy and paste these formulas and get the right answer there. I could do the same thing for perturbation theory. If we do a thing called MP2, that energy is right here. But coupled cluster, runs. Here's my correlated CCSD energy. I'm going to copy that guy, put it here. Okay. You can see my correlated energy is below my Hartree-Fock energy, which is good. Last thing I'm going to do just for illustration purposes is do the carbon and hydrogen atoms. As C and H, CCSD, JF, CCSD, sure I leave enough lines. This link 1, by the way, in the input file means do one calculation and then do another calculation. So we're going to save that. We're going to run that calculation. Everything ran fine. Okay, so the first part is the coupled cluster total energy of carbon atom in the ground state triplet state. Runs. I get a Hartree-Fock energy, which I can use for my Hartree-Fock calculation. I get a correlated energy from coupled cluster, which is lower than that. Lower than the Hartree-Fock energy, which is what I want. And over here, in the second part of the calculation, runs, we're done. We start the hydrogen atom again. Blah, blah, blah. There's my self-consistent field energy. And because hydrogen atom has just one electron, there is no correlation energy for this system. E2 is 0. As I say, there's no correlation energy for this system, so I get exactly the same energy from the CCSD as I did from Hartree-Fock. That's always true for any one electron system. And now I'm done. I can get the same atomization enthalpies here and here, and I can do the same heats of formation here. Something's a little goofy here. B7, B5. And okay, what do we have? We have the DFT works pretty well. Coupled cluster doesn't quite match the DFT result, and Hartree-Fock theory is really not that great at reproducing the experimental heat of formation. And that's consistent with what other people have done. If Hartree-Fock theory, if this method worked well for chemistry, computational chemistry electronic structure theory would have stopped in the 1950s, because in the 1950s people knew how to do this. Since then, we've been working on how to do this and how to do this. There's perturbative triples and other things we can do to improve this number. There's some error cancellation, which is why this one is better than this one. We can talk about all that later. But the take-home message, Hartree-Fock theory is not so great. Coupled cluster, if we added perturbative triples and did a large basis set and did all these other things, would be really spectacular. DFT does pretty darn well without too much extra work. So that's a good thing. So with that, we will close, and I hope you enjoy doing this yourself.